Hello everyone, greetings of the day. I am Madhvi, a student of software engineering. I am currently pursuing my degree from Chitkara University. In this video, we are going to discuss the task 9.3D of SIT111, which is about the implementation of the hack CPU. The central processing unit, that is, the CPU, is the centerpiece of every computer hardware architecture. It is the actual hub of all the computations being performed in any computer architecture because this is the part which contains the ALU in which all the computations of the machine takes place. Also, the CPU is where all the decisions are made about which instruction is to be fetched and executed and when the same is to be done. Talking about the hack CPU, let's first look at the abstraction of the hack CPU. The hack CPU is a 16-bit processor which is basically designed to execute to firstly execute the current instruction. Basically, now it's like that all what we have designed and learned till now theoretically, the hack CPU takes all that together and makes everything actually dynamic. Further, the CPU figures out which instruction is to be fetched and executed next. Of course, it follows the fetch, decode, and execute cycle that we have studied previously. This is what the CPU's abstraction is. Now, about its detailed specifications and interface. First, we need to remember that the hack CPU works in accordance with the instruction memory and the data memory when implemented in the hack computer, which we also did in the task 9.1p. Moving on to the interface of the CPU, this figure shows the input and output pins in the hack CPU, namely, firstly, the 16-bit in M pin, which is actually the value of the currently selected data memory register. This is the value that the CPU is going to operate on. The next one is the instruction, and as its name suggests, it tells that what operation or what instruction is to be performed on the current value. The third input is a single bit reset pin which will restart the signal. On the right hand are the outputs of the ALU. If the ALU wants to write something on the data memory, it needs to specify three different things. First, what is it that we want to write, which is stored in an output pin called outem. Second, where is that being written, that is the address of that location which is specified by the address M pin. And third is a load bit which enables the data memory to write the operation. Further, the most important output pin is the 16-bit program counter PC pin, which basically holds the address of the next instruction which is fetched and executed. Now comes the main part of the hack CPU implementation. This diagram is actually identical to what we have just saw before. We have 3 input pins and 4 output pins. Here, the symbol C represents the control bits which help in building connection between different parts and thus makes the CPU functional. This interface comprises of what we have built previously. We have two MUX16 chips, A and D registers, and an M register, the ALU, and the program counter. Whenever any instruction comes, if it is an A instruction, then it goes directly to the MUX16 chip and gets decoded and executed. And if it is a C instruction, then the ALU decodes it and then it goes to the MUX16 chip to get executed. Then we see that the inputs of the ALU have two sources. One is the D register and the other one is either the value of the A register or that of the selected memory register, which is decided by the MUX16. Then the ALU computes whatever it gets and produces an output which is fed to the A, D and M registers. Further, following the reset button, uh, its function is to run a program if reset is equal to 1, that is, if it is selected. Moving to the program counter, Its main function is to take care of the jump bits, which are the last three bits of any instruction. Now I'll explain the HDL code of the hack CPU implementation line by line. Looking at the interface, as told earlier, the CPU has 3 inputs and 4 outputs, which are the same as explained previously. A 16-bit NM pin, a 16-bit instruction, a single bit reset pin, which when set to 1 restarts the execution of the program, else if it is set to 0, the current execution proceeds. The outputs are a 16-bit out M, a single bit load named write M, a 15-bit address M, and a 15-bit PC instruction. The first NOT gate is used to check if the instruction coming into the instruction memory is an A instruction or a C instruction. The next one tells if the instruction is a C instruction or not. Then the AND gate checks if the output of the ALU is to be stored in the A register, which will happen if it is a C instruction and its destination bit is 1 and its first destination bit is 1. Then a mux16 decides what is to be stored in A register using the output of the AND gate. An OR gate is then used to set the load of the A register, which will be 1 if any one of the A instruction or the C instruction have to be executed. Then an inbuilt A register is used, which takes the input from the mux, load from the OR gate, and gives the output. A mux16 is then used to choose between A and M registers, which go into the ALU as one of its inputs. The 12th bit of the initial instruction goes as the selection into the mux16. When the C instruction is decoded by the ALU, its 4th bit goes into the AND gate, whose output is then sent to the D register as its load bit to give the output D out. Here also, we have used the built-in D register. The output of the D register and the chosen A or M registers uh, are then sent to the ALU along with the six control bits from the initial instruction, which tell the ALU about the computation to be performed. The output of the ALU is the result of the computation, and here again a built-in ALU chip has been used to avoid any kinds of errors in the code. Then the OR16 chip and the AND gate tell if the instruction is to be written in the memory or not, and if yes, then they specify the location where it has to be written. Now the section of program counter starts. The first 6 AND, OR and NOT gates are now used to tell the values of jump to the program counter by reading the last 3 bits of the initial instruction. These gates include the conditions of jump if equal to, jump less than, jump greater than, and jump less than or equal to. Then the OR gate tells this PC, the program counter, to jump to A if it is greater than or less than or equal to. If the jump is greater than or less than or equal to. Using the AND gate, we can say that if the instruction is a C instruction, then the program counter has jumped to A and then the load of the program counter gets enabled. And if this is not true, then the program counter gets incremented by 1. Finally, the built-in program counter chip is used to instruct the CPU that after executing the current instruction, to which next instruction the jump has to be taken. So that was all about the implementation of the hack CPU. Hope I was able to explain it as expected. Thank you.